Last couple of weeks, how's everyone holding up? Why? What's up? Oh, yeah, that time of the year. Uh, yeah, I've been seeing a lot of U-Haul trucks around. Um, no, I meant just generally, course-wise and homeworks and stuff like that. Okay, okay. Um, I know you guys have other classes. How's the workload? Yours was robotic algorithms? Oh, ML. Okay. Uh, does that have a final?
It did have a final. It was only a 6 week.
Oh, right. Yeah, okay. Well, what did you think about that 6 weeks?
Pretty fast. I think the instructor did a good job that amount of time. You don't really know. It was under which I think is yeah, he did a good job.
Cool.
6 weeks. 6 weeks is probably too fast for
Yeah. I think it took me about 6 years to finally feel like I understand what goes on. Okay, 34, I guess, yeah, that's close enough. Um, so I guess before going into optical flow, which is what we're going to do today. I think some of you have projects that sort of tangentially deal with this. There's people doing deep sort, object tracking. Um, so I believe that those are built on the principles that we'll look at today for optical flow. This is so. We're going back a little bit to all of the pre-machine learning sort of stuff that we were doing initially. But we're done with all the ML, DL kind of vision that we were going to talk about. Diffusion was the end of that sort of arc. And while there's even for this, there's a really good deep learning model, which is included in Torch Vision, and that's called Raft. But we're not going to go into all of that because it's a really vast space if I had to try to cover all deep learning based vision methods. And it's useful to know how things were done before deep learning was a thing, because there's a lot of intuition to be gained from understanding these things, which is why we're going back to this. The plan is that there's two algorithms. We're going to talk about one of those today, Lucas Canade. There's another one, Farnback is how you say it, I believe. I'm not sure. I have to look up how to say the name, but that I haven't decided if I want to go into that or if I do something different from optical flow or if I do like a review for finals. I will be doing some sort of review the class before the final. I'm not gonna do anything new on the Tuesday next week. Uh, yeah, so I mentioned a couple of things like tracking objects, so that should give you some sort of hint of what optical flow should be. But I would like to hear guesses. So there's two things to the name. There's optical and there's flow. So optical, I think there's pretty nothing surprising there because we're talking about vision and image processing, but flow should indicate, yeah, movement. Um, as always, slides from Dr. Redmond. We have our old boy Bender over there against a backdrop of a mountain and the sun, or uh, Bender goes for a stroll, moves to the right end of the frame. Everything else in the frame is unchanged. So he's moved and pixel values that would have corresponded to where he was initially should have shifted by some amount, leaving everything else the same. So that's one kind of motion that we could take into account. Any other kinds of motion that you guys can think of? For stuff to move in a frame, what are the things that we can move? Can physically move the mountain, assuming it's a real mountain out there, and this is a picture of a real mountain, but yeah, you could move the camera. So you can pan the camera, which will introduce some sort of lateral shift or vertical shift. You can also, yeah, but so rotating it, panning it, all of those would be in plane movement, right? So there's no like scale kind of distortion. That would come from moving the camera towards or away from the scene that we're looking at. So that will change scale. In this case, our pixel values are sort of moving outward when you compare it with the original scene that we were looking at. In pan, they're all just linearly shifting by the same amount. This is optical flow is basically a way to represent motion in a frame. And the way we do that is we can represent it with vectors for each region in the image that sort of point to where pixels are moving. This is, I believe it's the person's playing Pong or something. If it loads, we'll be able to see it. So yeah. When his head moves, you're able to see those vectors light up, um, and the intensity changes with the size of the vectors plotted change with the intensity of movement. Yeah, you would need some sort of one reference frame and one comparison frame, because there is that temporal aspect. You can't represent something moving directly in a single frame, uh, which is why we need pairs of images. Now, I already kind of spoiled this, but motion estimation is the broad sort of umbrella term that we'll use to say why we care about this. And some examples, this I think is how the sort algorithm's output would look. Sort or deep sort. I'm not sure because I haven't done those myself. But visual odometry is used a lot in robotics. It's one of the components of SLAM, I think, visual SLAM, and this stuff is also used in self-driving that is vision-based and not the camera-based rather than LiDAR-based. Uh, hmm, yeah. So there, I mean, Teslas also have LiDAR, I believe. No, they're entirely vision-based. Yeah, that's my bad. Yeah, so visual odometry, in that case, they have a whole bunch of cameras, and fusing information from all of those, they can, well, I don't know whether they individually estimate how each camera is moving. It's not really necessary to do that separately for each of them because you know the relative positions between each of the cameras and they're all rigid, so that doesn't change. But yeah, the problem statement here would be to estimate how the camera is moving based on visual cues that we're getting, which would be optical flow. So that is a trajectory of how the camera moved in the scene, and this would be top down um, within that environment. So uh, loosely, we have some sort of intuitive idea of what is necessary to um, get to optical flow. You need at least a pair of images to have. Oh, oh, right, yeah. Forgot my watch today. This goes in. Normally I have that set to quiet. Okay. Yeah, pairs of images with some difference between them. Uh, we can say that if they're from the same scene and that there's some difference between them, then it's because something within the frame has moved. So how to quantify that? Um, any guesses? I went back to the previous one just to, so what's changed in that pair? Okay, that the tree moved right. Um, what's the simplest way to um, okay, then edges, okay, that's a good start. Yeah, that's one of the intuitive ways that you would think of trying to solve this problem, right? Because panorama stitching, we got a bunch of features, um, and we were able to find where those features are in a second image that has some difference with it. So it's not really all that different from trying to solve this problem, right? Um, we have all these ways of representing things that would be common between two images. We know how to find them, and we're able to um, build representations to sort of index um, where in an image we're talking about. So we could apply some sort of feature matching, um, see where those same features have moved, and that tells us which pixels moved where, right? Does anyone see any problems with this?
So if it's not with the key point and still available in the next image, it will show that this key point is at this location.
I mean, you could probably have some sort of logic that says, well, if it, but let's say that corner, it's still going to be in the same place, right? In this one, even if it shows up as a feature in the second image, because it hasn't moved. So you could say that only consider features that are not in the exact same pixel location, or maybe within like 2 pixels of where it was in the previous image. Hmm. Okay. Again, I guess you could solve with some sort of thresholding. Let's assume that clouds are not significant um, for this particular case. So what if our guy Bender sort of, but by the time he gets over there, so he's not moving entirely rigid. His arms are going to be swinging. Um, it might end up in a different position if he's facing the camera a little bit more by the time he gets here, then there's no guarantee that we'll get the exact same features because lighting conditions might change a little bit. And then within that particular neighborhood, that whatever feature extraction algorithm we're using is looking at, it might just end up being insignificant relative to what's around it. And it doesn't describe the entire image, so it's sparse. We only get it at certain points of importance. And you guys experienced this while working on the panorama problem, right? Feature matching. It's not a deterministic exact. I mean, it is. It's definitely not as uncertain as doing something deep learning based, but there's still, you don't know going into it what exactly you're going to find. You still have to sort your matches, pick the best ones from them. So there's all of that to deal with. We got features in different places, so it's not great. And especially if you have to do that for every pair of images, if you have a video and you want flow also as a video the way we saw, then that's a fair bit of computation doing feature extraction on each of those. It would be simpler if we had a better way of applying something directly to an image that is global and not selective, like something that depends on feature matching um, would be. Feature matching, some of the good things that we've seen earlier when we talked about it was that it was scale and rotation invariant and lighting conditions. Some of them are robust to changes in that. Large movements it would be able to handle, whereas if we were thinking of something like a convolution filter that we could apply to the whole thing, then you're constrained a little bit by the receptive field of the filter that you're applying. So whatever is within the kernel's size is what you would get a response for. We need to come up with something better than that. So let's take the case of this cylinder moving to the right. What we can do is we pick one location that we'll keep monitoring as the cylinder moves to the right, and just keep track of all the pixel values that you would see at that location. So if you're only paying attention to that spot and the cylinder moves to the right, you see that it goes from dark to bright, and we're able to see that trend here. And we can plot that. So this is intensities versus time steps. So we are able to represent intensities as a function of time, intensities at a particular location as a function of time. Another way, another thought experiment. So earlier we moved our object. Instead of moving the object, if we look at different locations within the same image, so we assuming that the object is shifting right, we shift our observation point left, and we see the opposite trend. It's going from light to dark positionally if you look at where the values are. But the order in which we look at it is from right to left. So we invert it over here and plot the intensities. And that gives us the same trend. So these are functionally equivalent for what we're trying to do. And here, the assumption that we made is we already know that this cylinder was going to move right. So looking left made sense. We need a way to generalize the whole that process so that we can get this information from a single image.
This second, the object was not, it would definitely show the same. Because the pixel value would be less in intensity while we are shifting the location of observation, even though the object is.
Yeah. So we're able to get information from one frame that required 4 frames earlier. The reason I mentioned, yeah, it's not optical flow. Think of it as just another feature that you would then use for further something downstream, rather than directly saying that something has moved, because that we can't say for certain that something has moved within one frame itself. But this we're working towards a generalized algorithm. And the reason I mentioned it's not moving here and we're looking left is just that we could have gone up or right or diagonally or whatever. So just to sort of in the moment justify the choice of why we're going right to left here.
Light source of the image, if that moves, won't that affect the?
Yeah. Yeah, it will. The assumption that is sort of implicit is we're looking at something where motion of what we want to observe is significant when compared to its environment. So light source moving, if that is one of the aspects of the environment, then tracking movement either would have to include that motion if it's predictable. You would include that into your motion model somehow, or the light source moves, then just put an accelerometer on it, I guess. So we got this neat little trick to sort of simulate movement. So instead of moving an object, we can move our observation point and get what it would look like if the object moved. So Lucas and Kennedy in 1981 shared their algorithm, and we're gonna derive that or understand how they got where they got. So some notation, we assume that the object moves by delta p pixels over delta t time steps, and f is the function that gives us pixel values or light intensity before, and let's see, p and delta p, we have our observation point. Delta p represents the movement. This is our first image, and since there's a time increment, that's our second image. So t plus delta t we use to represent that it's a subsequent image, and that function will resolve time and pixel location to give us intensity of that location at that time. Now, one way that we can approximate this is using a Taylor series expansion, which to me, I automatically have this aversion to just trying to understand anything that has some named math. I've included a link to a 3 Blue 1 Brown video on how approximation is done using the Taylor series. It's the way I understand it is it's kind of similar to how we think of the Fourier transform that allows us to decompose things into different frequencies. So similarly, we're able to take any arbitrary function and approximate it as a sum of a bunch of polynomial terms. So you can represent it as a combination of a line, a curve with like one point of inflection, 2 points of inflection, and sort of add them all together, and that gets you close to the function you're trying to model. And yeah, okay, so that's the general formula to do the approximation. Oh, that should be subscript. That's my fault. So this is the format that it should be in, that I should be down there. That we have a coefficient corresponding to each term. So for first order, we only have the highest power that we care about is 1. And this is, once unpacked, functionally equivalent to the equation of a line. It's similar enough that we can just say, oh, we're going to think of our function as a line for now, because in this region it's close enough and we don't really care about the negative intensity space. And it's equal at x. So using that first order approximation equation that we saw, where it was similar to the equation of a line, we can substitute in our x term with p minus delta p plus just a constant, and that's approximately equal to doing the same thing on this side. We substitute that in. MP. Okay, no, we didn't. But we're only dealing with the left side for now, so we expand this into the parentheses. And space, what was that? So, okay. Man, these colors are throwing me off now. It was helpful when I was looking at it on a smaller screen. Okay, let's see. So MP, we expanded the slope term into change in pixel position, and there's a constant that we're not worrying about at the moment. And just because we have the same term on both sides and we can do it, we're going to subtract. No, we have this on one side, and we just throw that in there. So that is something that would cancel out, so we can put it in there without causing any problems. And we plug in our mx plus b line equation. We're dealing with pixel values instead of x values, so we call that an x over there. And we're able to cancel out MP plus B, which is what this would expand to if we do the substitution. And that leaves us with just this one term being approximately equal to change in pixel intensity for the same pixel over time. So the only thing that's changing between these two is the time step, and we're able to approximate that with that term. So we already know what these are. We want to know change in pixel position, and this is slope. Slope we get using by calculating the derivative, and we already have a good way to do that for images, which is getting the gradient. So we can apply our trusty Sobel Pruitt operators. Using the same logic, we can figure out the slope of how pixel intensities are changing and use that to guess the change in pixel position. So just quick recap of getting derivatives. We use change in pixel values along one of the two axes that we're dealing with, and use that to calculate the gradient. So we can plug in our operator to calculate the gradient along. This again would further expand into the x and y operators that we normally use, and this is the combined gradient. Plugging that in, not much has changed. It's just the slope term. We replace that with our combined gradient operator and just rewriting all of that stuff without the vector notation. We have gradient along x, negative gradient along y, giving change in x position, change in y position. And we're resolving this also to its xy coordinates, since that represents coordinates, and time steps remain unchanged because there's no further dimensions to it. We call our change in x, change in y, we're just rewriting that as uv so that it's a bit more compact. This whole mess of a situation, we say that that's intensity at time t given coordinates x and y, intensity at time t plus delta t given coordinates x and y. So it's a lot more readable now. and uh, we're no longer calling this approximate, we're setting it to equal so that we can then use that to solve for stuff, and this negative sign gets moved on the other side, and we flip the order around. So solving for u and v is what we want, since we want change in pixel position. I already skipped ahead by one slide, so you know that it had that giant impossible over there. But why would it be impossible? We are trying to solve for how many variables? 2 variables. How many equations do we have? So that's not good enough, right? One equation, 2 unknowns can be solved. There should have been, okay. So we still have some work to do, which is where we dig into what the image domain significance of these changes are, and whether we can do anything else that's clever to tease out some more information. So gradient along x, gradient along y would give none of your vertical edges would show up, obviously, because you're going low to high. So anything that's along the same axis would just be a constant value. This we're thinking about brightness per x pixel, brightness per y pixel, and if we combine both of those, and well, this we have our change in x position, change in y position, and we're adding the 2 of those together, which is equivalent to just comparing 2 positions directly, or 2 time steps directly. So this is taking the difference of 2 time steps, and this is getting that same information from one frame by looking at 2 gradients and combining that information. But we still only have one equation, 2 unknowns. So one assumption that we can make is that for any pixel that we look at, pixels in its immediate neighborhood will also have similar changes in x and y positions, since we can assume that the whole thing is a rigid object, and all parts of it will move together. So once we make that assumption, we can expand our observation target to its immediate neighborhood, which is the other 8 pixels surrounding it. So that now gives us 9 equations and 2 unknowns. This is overspecified. We would like to have a linear algebra representation so that we can solve this as a series of matrix operations. We put all of our gradients in our S matrix. We have our change in position for x and y, which we're calling u and v, and that's what we want to find. And then we have what our intensities are, so we can sort of remap all of the information here into this system of matrices. And this then becomes something that we can attempt to solve. So the least squares solution would be moving that over to the other side, and then trying to calculate delta p by inverting the S term. So we don't necessarily know that this can be inverted. Uh, so we need to figure out something better. So first thing that we need to know is whether it can be inverted or not. When we have symmetric matrices and you what's going on over here? We have our S term that's the transpose of it, and we are multiplying its transpose with itself, and that term is symmetric, so it then gets decomposed with we take the determinant of this whole thing. This is similar to the eigenvalue, eigenvector decomposition stuff that we looked at earlier. And solving for this whole thing, um, if either of those are negative, then it cannot be inverted, and we can't solve it. So this is also kind of tricky to work with. We need something a bit more robust that gives us an easier time. Here, we are considering what the pixel values on each face are, and there's no variation, so no gradient. Um, Once we get to the edge, we would see a horizontal gradient, allowing us to capture that edge. But when we look at our vertical gradient, we get nothing over there. And this gives us both of those. So that brings us right back to one of the first things that we accepted is that corners make for good features. But we already talked about why feature matching directly wasn't good. So we're incorporating that into the idea of optical flow. And the naive looking at one pixel or the immediate neighborhood, that changes when there's lighting changes, when there's large movement, when there's specularities is when you have like really bright spots, or if you look at a surface that shimmers or glitters, then when it moves, the intensities that you would capture are not going to be in the same place. Um, and trying to apply it directly on a region that doesn't have any variation in gradient, even if you have a larger neighborhood, you can't really estimate flow. So basically, this approach only works when you have good gradient information. So it sort of corresponds to um, locations that would otherwise be good features, and in all the other regions you just wouldn't get any flow estimate. So we're not able to solve it in those cases. And that finally brings us to the aperture problem. So let's say this line moves up and to the right. So if you try to apply our Lucas-Canati approach, looking at one pixel and its neighborhood to see where the line has moved, well, within the neighborhood that we look at, everything is still the same. Nothing's moved. Still the same, I mean, like vertically, sorry, I misspoke. The upward motion, we're not able to capture that because we're restricted by the window within which we're looking at. So what should have been an upward diagonal movement gets resolved by the algorithm to just a rightward movement. And this is an example of a case where you would see something like that. Now, since we're able to see the whole thing, we know that it's a cylinder that's spinning, and that pattern is going upward, and combined, the motion that we see is diagonally upward when you, because even when we look at it, we're if we only look at that part, then you wouldn't be able to tell that it's part of a 3D structure that's moving differently, because we're only seeing a 2D projection of what's going on within a small region. So that is a result of our aperture constraint. So the aperture that the algorithm considers when estimating motion is resulting in a false estimate of direction. One way to improve it is we do it iteratively. We first get one set of gradients and then make an estimation using that. Then we hold on to that information across time steps and keep doing it multiple times. So that allows us to hold on to some context of what's going on by chaining them. Another way is kind of like our Gaussian pyramids, where we solve the problem at multiple scales, run Lucas Canati on a small scale image, upsample it, then run it again, upsample it, then run it again. And hopefully the motivation for doing that is what would be within your aperture changes based on scale, right? So if you downsample an image, then it's effectively the same as increasing the aperture of your optical flow estimation, and vice versa. When you upsample the image, you're estimating flow in a smaller region. Your filter gets applied to a smaller, you're shrinking your aperture by upsampling the image, and that will give you a different set of responses for each location. So just recapping and tying the whole thing together with a bit more detail. The initial assumption is that the brightness of a pixel will remain constant when it moves from frame to frame. And by pixel, we're saying one pixel location should exhibit the same intensity value for the same position. But when there is movement, we want to try to estimate that using the assumption that values corresponding to one location wouldn't change even if the object moves. It moves to a different pixel location, but the value will remain the same. That's the initial assumption. We have our function that gives us takes change in position and time and gives us intensity and does the same thing for time steps. Delta P is our optical flow vector, which we represent with the gradients along x and y. We try to approximate what the solution for this would be using a first order Taylor expansion. We start by expanding the left side, where the spatial gradient of the image would be partial derivative with respect to x, along the x direction, x along the y direction. We have those two components, and we combine it, and so there's the FP and time term, and then the spatial gradient with the optical flow vector, which is what we want to find, which tells us each motion component, x and y, and rearrange everything a little bit. Keeping this on the same side, we throw that over there, which is the same as subtracting that from both sides. And then expand it. So gradient along x, gradient along y, these would resolve to, okay, the fx, y, t, and then time step. And then, yeah, so we have a way to estimate our gradients. So we replace these terms with our gradient estimate approach, where we apply something like Sobel or Pruitt, plugging in window size, because this, I believe, 2k plus 1 would come up because, okay, that's just the number of responses that you would get, since if you have a window of size 2, then that would be 2 by 2. I'm not sure why the intuition for why that series has to end at 2k plus 1. I'll check that and put it in there before I'll upload my slides. But then we rewrite this whole thing as a series of matrices, linear systems, so that we can apply least squares to solve it, where we have our gradients, our individual flow vector components, and the change in position over time. And then we solve that, first checking for the eigenvalues. If they're negative, then it can't be solved. But if not, then we can try to solve it iteratively for large motion, or do it multi-scale, or combine both of those. So this, while the approach, while the algorithm, the way it's formulated is in a way that it can be applied densely, but the issue is, since it relies on gradients within a neighborhood, you only get usable responses where there otherwise would be good features. So it's effectively sparse, even though it's designed to be dense. And ideally, we would be able to, the ideal version of an algorithm that gives you optical flow would work for every pixel in the image. So It's formulated as a dense algorithm, but only works on pixel locations that would correspond to good features otherwise. So in practice, it's sparse. And yeah, I'm not going to go into Farnbach today. I don't know that I will necessarily go into that. It's either I can either do that or calibration. Feel like those are the kind of things that a longer course would better accommodate. Between doing a review on Thursday for the final and on Tuesday, or okay, so Tuesday I'm definitely doing review for the final, right? That's that I've decided. What I haven't decided is what to do next class. So would you guys prefer that I continue on flow, or pick something else, or do review? I feel like 3 hours of review would be too much. Yeah, isn't the final next week? Hmm. So the final is the third class from now, right? Fourth? Are you including today or? Ah, today is Tuesday. Okay, there's a Thursday, Tuesday, and a Thursday, right? Third one?
Next Tuesday.
Oh, is today a Thursday? Oh, yeah, okay, okay, that makes a lot more sense. Uh, okay, yeah, then next Tuesday I'll cover Farnbach maybe. Or actually, no, Farnbach would still be required to put raft into context. I was thinking of maybe expanding on this a little bit, uh, like a quick 5-10 minute code demo, just so that everything in here makes sense, followed by raft, which is a deep learning model that estimates optical flow. That's one option. The other thing I could do is Farnbach, which is a dense optical flow algorithm. And Raft after that. Okay. Yeah, either way. Optical flow, I'm gonna continue. The very least that you'll get is some sort of demo that puts all of this into context, because uh, equations, I don't know, it's just a lot easier to tell what something is doing if you can see it doing the thing. So yeah, that's it for today in terms of material. If you have questions, I can go back, or if you have questions about homework or the project or whatever, I could take those. Oh, yeah. Yeah.
We expected us to.
I'm not gonna ask you anything that's not on the slides.
So it would be
And
architecture questions.
yeah, yeah. So for deep learning kind of math, I mean, giving you some sort of very basic architecture and asking you to do the forward pass and propagate backwards. I think that's a one kind of question that is asked in like deep learning or ML classes, but I don't really see the point of testing you guys on that because we're not dealing with that directly. We only care about it as a means to an end. So the just visual intuition type math, what gradients are, where you would use those, why we care about them, feature map responses, stuff, just the kind of math that has been on the written parts of homeworks. I'm not gonna throw everyone a curveball and give you like weird math because I mean, if it's any comfort, you guys, I've mentioned it like verbatim that I'm not a big fan of math. Uh, so that should reassure you that I wouldn't be inclined to test you guys on a lot of math, although it is required. And at the very least, understanding what's going on under the hood, even if you can't like um, derive equations directly, just the significance of what they all correspond to and how they relate to each other, the chain of intermediate representations that um, is something that you should understand for all of these, even if you can't write the formula and stuff off the top of your head. If there is anything that I want you to like solve, and it's some non-standard math, I'll include the formula in the question. Like what was it? Histogram equalization, the CDF and all of that. I'll just put that in there because you're never going to do those by hand. It's always going to be part of some code anyway. And even in code, it's usually implemented within like NumPy or OpenCV or whatever. So you wouldn't be dealing with that even at that level of abstraction. It's like 2, 3 layers hidden away and you don't even have to think about it. So I'm not going to go all the way down to the lowest level, but just enough that you know what's going on within the most abstracted version of it. Just so that in case you try to take a function and apply it to something and it's not doing what you expected, you should know why it's not doing what you expected or just what the possible reasons for something not functioning as expected might be. That's about it.
Like general, like can we get a read or something so that we can understand what kind of question could be asked, like a week before, so that we have like a couple of days to look through it and just understand what like in what
Like sample questions?
something like that. And just to give a ballpark idea, like something these can be asked or these type of questions can be asked.
I mean, the kind of stuff that was on the homework, that the written parts, similar to that, maybe like one tiny notch more difficult than those. But yeah, I won't have you like jump through hoops to solve anything. I was also planning to post this on Piazza yesterday, but there's I haven't decided how many sheets I want to let you guys bring, but cheat sheet. 3 sides is what I was inclined to announcing, but enforcing that would be kind of tricky because 3 sides is 2 sheets, four sides is also 2 sheets. So I'm either gonna let you bring one sheet or two sheets. I feel like if I ask you to bring one sheet, you'll um, fixate too much on trying to fit as much in there as you can and end up like not absorbing the stuff while you're making it. And I don't want you to have to stress about not having enough space for all the stuff you need. So two sheets, four sides is what I'm leaning towards. And I think making your own cheat sheet's a pretty good way of getting information to stick. Um, yeah, and yeah, calculators are okay as long as they're not an app on your phone, but are a physical device. Um, yeah, I would like to do lockdown and give you like scratch paper to solve stuff and put it there. Uh, the challenge with that is, I mean, the questions are going to be the same even if they're not in the same order. So towards the end of the exam, I feel like a lot of information will propagate. It's just easier if the final format of answer that you input is something that you can either like click or just type in versus if it's you having to solve it. Yeah, I guess I could just ask for your scratch sheets also. And if the corresponding um, working is not in there, then you'll have to chat with me about how you got to that answer. Uh, Lockdown. Yeah, well, I guess I'll make it optional. I'll put a poll on Piazza. Whoever wants to do lockdown can do that, or if you already know you want to do pen and paper, then we can just do that directly. Does that sound like a reasonable plan? Okay. Yeah, sample questions. I mean, I don't have a final made yet, so any questions that I come up are with are first going to go in the final, and then I'll have to figure out more to share with you as a sample. Uh, yeah, I don't really have anything else beyond that to talk about for today. Also, don't want to overload you with new stuff considering the finals approaching. And this is to sort of reinforce some of the foundational things that we talked about before we got to the deep learning bits. So I wouldn't dwell too much on the math, even though it is important to understand what's going on over there. I'm not going to ask you to like solve flow or like derive the approximation and stuff. Yeah. Well, there was one other thing that I wanted to bring up. Yeah, no, that's it. You guys are free to leave if you don't have any questions or whatever. And I'll see you next week, not in 2 days like I initially thought. It's because I work from home on Wednesdays to prepare for class that made it feel kind of like a Sunday because yeah. Late. This isn't even the first time you're asking, right? You've asked me, I think last class also. Yeah, you've asked me this at least once before. That much I remember. Regardless, whether you have asked me before or not, yeah, I mean, there's only like 3, 4 classes left. I'm not gonna let you do this again.
Right. Or
Yeah.
three. For enlargement filter, there's last requirement for to do 3 additional filters.
Yeah.
What does it mean?
I mean, instead of just like the way I didn't give you a filter, did I? So the way I did it when I was building the solution first before taking stuff out was I made the eyes and the mouth big. You can instead of that, so not 3 types of enlargement, but just 3 types of warping filters and just warp different things like warp the entire head maybe, or just one eye, or make the nose smaller,
Okay,
or
so
something
that's the
like that. Yeah, that's all. Or any other like filter type, not overlay type transform that you can think of. Um, so the warping, you have your landmarks, and then you're applying some operation within a region around each key point that you care about, right? So just some transform of that
You
kind.
have to apply a filter on or a mask on that warp region.
Uh, you're asking me about the
Yeah,
enlargement
that-
one
that-
specifically,
yeah.
right? So
The last
how far did you get so far?
getting an warp image. I'm able to,
What is
I mean,
getting
I'm-
warped? Is it like the whole? Are you applying it to the whole
yeah,
image?
the whole eye is getting warped.
Okay,
And I'm
and
able to get something like this eye.
fisheye just
That's the
around
only
that
thing,
region.
yeah.
Yeah. So that is the expectation. And so doing that for the eyes and mouth, all of that is a subjective choice, right? You can choose which
Anything,
landmarks
yeah.
you want to apply those to. So just
So there's 3 different combinations of which landmark we want to.
yeah. There's no expected output for that, no rigid expected output, which is why I'm asking, because I want to see some variation across what everyone is doing.
Thank you.
Yeah, you're welcome.
So there is summer camp next week for UB
Okay.
for the undergraduates and participating. So not participating, but there's a
You've been asked to join basically.
Okay.
camp
Conducting
counselor,
that.
so we'll not be able to come to class. So is there any way that we can take the quiz before or after?
When did you say this is?
Next
So
5 to
both
5 days
uh,
from 9 to 4.
9 to 5. Yes, 9 to 5.
9 to 4.
have you
around 8 or something?
have you missed any quizzes yet?
Just one. That date was like very rare.
I can't do that's kind of the point, right? I mean, you not being able to attend, I get that.
We will be here in Davis and like right besides Davis.
What are the timings for that?
9 to 4. So we can get before as well if it's fine.
Mm. I'll think about it. Send me an email
Uh,
and I'll figure out something. Yeah. Any other
so
questions?
about the final, will it be kind of like an objective or like it will be subjective?
I mean, you'll have to like solve stuff. Some questions. So if we do end up going the lockdown or paper you choose route, then you can expect questions that will have like a numeric answer or something.
So you have any other like objectively or subjectively as your choice.
No, I'm saying that the maximum extent of subjectivity would be
Yes, sir.
Numeric values, but I wouldn't ask you to like write sentences as answers.
Got it.
So only when there's something that you have to solve or whatever, I might frame it in a way that there's no options to pick from, but you just have to put a number value as the answer. That's about it. Yeah.
So we have to.
What?
We just came at like 11:50 and this.
11:50? Huh?
No, sorry, 10:50.
I think he has a post like he
Yeah,
posted-
yeah, the fix.
No, not fit. The
Oh.
GitHub thing. He said there was some issue. He gave a new link.
If you already cloned it and were able to see the assignment, then you don't have to do anything different. It's so what happened is, hey, is there a class now or? Oh, yeah. Yeah, you're welcome. So GitHub Classroom, they changed the way people cloning or accepting an assignment, how it gets added to their account as a repo. Earlier, it used to be starting from a template repository, and after that, it switched to forking it and forking the way they're doing it can't be done from a repo that has more than one commit. So this particular assignment, when I made the template, it had like 3-4 commits in its commit history. So for people who tried cloning it, all they got was an empty repo, just a README. Yeah.
I just want to ask.
Yeah. So if you already had everything, then you don't have to do anything different. That change in the way they do it, that went into effect, I think, yesterday. So people who tried cloning it yesterday or try to do it going forward will run into some issues. So I figured I'd just squash the repo and make a copy. Since I can't edit what repository it uses as the base once, even one student accepts an assignment, so I had to make a second assignment as just to reference that other repository. Yeah, you're welcome. Hey, do you have a question or something? Or? Okay. Okay. Do you need help with that or?
That they have going on is not having an issue. And also that the work is due on Sunday.
Yeah.